So I think, Sheila, I should introduce you, although you've been talking, but people should know who you are and what your background is a little bit. We're very fortunate to have someone who's not only has dedicated her life to education, but has also done research in geology. So I don't know if I didn't tell you I was going to ask you to say this, but if you could just say a little bit about both your experience as an educator and a little bit about your experience actually in the field, and then I'll let you jump into your lecture and tell us all about Oregon geology.
Okay, well, I got started in geology. I never dreamed I would do this, so I've been in education since 1985, and very involved in it. I was I've been very involved in all levels of education. I went back to school later in life after I raised my family, and had to take a geology class, just very much like a lot of my students. I had to take I had to take science, and I picked geology. And after my first class, I was hooked. I had lived in several places around the country. I had traveled a bit and seen the ocean in different places. And my very first class explained all that I'd always wanted to know all my life. And I just been hooked on it. So I've been teaching at the college level for 20 years now, and I'm happy to be here. So what I'm gonna do today is give you an overview of geomorphic provinces. So we'll focus on Oregon, that great state of Oregon, and we'll focus on the different regions of them. I want to show you some pictures of what the different areas look like and what they mean. And then I've got, as you might be able to see behind me, I'm going to pull it closer to the screen, but I've got a felt board of Oregon. So when I'm done with the PowerPoint lecture, I'm going to put the pieces on the felt board in the order that the state formed. And you'll get an idea of how this place came to be. So do you want me to go ahead and start now?
Please do, thank you.
Okay, now let's see if I can share the screen since we had that previous issue. Can you see the screen that says Overview of Geomorphic Provinces? Okay, everybody is mute, but I'm getting a few, and I can only see a few of you at a time.
I can see it.
Okay.
I can see it.
I can see it.
Okay, good. Then I think we did that right. Okay, I'm pretty experienced in this since I've been having to teach my face-to-face class via Zoom. So, okay, what I'd like to do here for you is give an overview of the geomorphic provinces of Oregon. Now, sometimes these are called the physiographic provinces, and sometimes they're called simply called the geologic provinces, but the state is broken up into several pieces. You might be familiar with them. This is a drawing out of Bill Orr's book, and this has also been used on the Dogami website to show the different regions of Oregon. Okay, and so every state has its own geomorphic provinces, and Oregon has quite a few of them, as you can see. So what I'm going to do is highlight each one of them. We're going to kind of go roughly in order that the state formed. And I'll show you a geomorphic province is one where there are similarities. Areas can be grouped into a province based on similarities in the rock types, and that has everything to do with how the state formed. And so I'm going to go through these one by one and give you an idea of what they look like, and then give you an idea of the process that formed them. And then we'll kind of put it all together on a collage on the felt board behind me. Okay, so let's start with the oldest part of the Oregon, and that would be the Blue Mountains, which we had a fantastic field trip last year to the Blue Mountains. And it's in the extreme northeast corner of the state. And the Blue Mountains are, the province is named the Blue Mountains after one mountain range, but there's many mountain ranges there. So we'll look at the beauty of the Wallowas is just incredible. Okay, this is a picture of Zumwalt Prairie, which is a high lava plateau of Columbia River basalt overlooking the Wallowa Mountains in the background. And it is so iconic that looks like paintings. In fact, I think this one is a painting, but you just get an idea of the extreme beauty of the place. So the mountain ranges there are incredibly beautiful, glaciers, carved out by glaciers. But just as importantly, the eastern portion of the Blue Mountain region it has the John Day fossil beds, which is a world-class collection of fossils. Okay, there's almost no other place in North America that has such a complete record of mammals from this time. So they've got a wonderful, in fact, our field trip the year before was to the John Day fossil beds and the area around there, the Clarno Formation. Just incredible collection of fossils. You can see plant fossil here in the back. You can see mammals and so forth. The painted hills are also an attraction. And what this is, you know, now most people think fossils form, and certainly marine fossils form in sandstones and things settling to the bottom of the ocean, or maybe in getting stuck in a peat bog or something like that. But the John Day collection of fossils in the Clarno is the result of extreme volcanism. And we don't think of volcanics as being a medium that preserves fossils. It's just, but it is. When you have, you know, hundreds of feet of ash being dumped on an area all at once, you do a wonderful job of killing all the animals and then also preserving them in an anoxic environment where they can be preserved. So as the result of the volcanism of the state, we've got this incredible fossil collection. Now the painted hills shows you the layers here. So you can see layers of ash that were dumped on an area, and then soil developing on top. These red streaks through here are soil layers, and then more ash and soil. You know, soil develops after a while. So we've got a whole sequence here, and they're all highlighted beautifully in the painted hills. Another place, this is Picture Gorge, where the John Day River goes right through here, and it exposes all the rocks. You can see the layering and the stratigraphy of the area. I'm looking at a lava flow up here. This is actually the Rattlesnake Formation up here, capping off this whole hill and protecting it. Let's go to another one. And the Clarno Formation, we went to see the Palisades. These are lahars, which is a byproduct of volcanism. Hot ash mixed with water and flowing as a slurry. It also preserves a wonderful collection of fossils, and that's also part of the John Day area. Everything can be seen here at Sheep Rock, which is just a little bit northwest of Picture Gorge. And but here we see the layering. Okay, so we're looking at layers here. In fact, this is the Turtle Cove. Remember, you can actually name these layers. These are all John Day layers. Clarno layers can be seen down here at the very bottom. So Clarno happened, then the John Day, and then the whole thing is capped off with some basalt here. And we'll talk about the origin of the basalt too. So a lot of the Blue Mountains is covered by basalt, and basalt, this layer up here at the top, this dark layer, is the basalt that covers the whole thing, and then we've got an ignimbrite on top of that. So we've got a whole layer cake here, and that's what I'm hoping to show you. I'm showing you scenes in different areas of Oregon, but when we do the felt board, I'm hoping to show you the layering and how they all formed in roughly the order that they formed in. Okay, so let's go on to the next area. That was everything. The John Day area is right in here. So, but this whole region is called the Blue Mountains. But let's go to the opposite corner of the state, and we have the oldest rocks here as well. So if we look at this area, this is the Siskiyou Mountains. I've got Bolin Lake in the foreground here. This area was heavily glaciated during the Ice Age, and so we have lakes up in the head of these glaciers called Tarn Lake in a cirque, the uppermost portion of the glacier. So the mountains have been sculpted by the beautiful glaciation, just as it has in the Blue Mountain region. Okay, Siskiyous are also home to ophiolites, and so we actually, GSOC had a wonderful trip here a couple years ago where we looked at the Josephine ophiolite. That is layers that used to be ocean floor that have been now pushed up onto land, and they're mining districts because they're the source of gold and other chrome and other important elements, very, very important. So, and that was all because it was ocean floor that then was pushed up onto dry land. Okay, this area is also region to the Oregon Caves, and this is a place very dear to my heart. I lived very close to the Oregon Caves for many, many years, and then after I became a geologist, I got a chance to go back there and actually lead the tour leaders, educate the tour leaders on what the Oregon Caves are. So the Oregon Caves are made out of marble, unlike most caves in the world are made out of limestone, but marble is metamorphic limestone. So what we had here is we had an area that had a shallow ocean, and it had a limestone bearing rock, limestone rock. But then in the folding of the development of the Klamath Mountains, the folding turned that limestone into marble, and now the groundwater has dripped through it and carved out an incredible cavern system. So the Oregon Caves are a highlight of this region. And this region is also known to lava flow. So we're looking at here a lava flow from Table Rock Mountain near Medford. And you might have seen this if you've driven down I-5 to California. You see that, and this is a lava flow capping off an area below it. So a lot of variety. Now, I want to focus, the next slide focuses on both the Blue Mountains and the Klamath Mountains and how they actually formed. But now, when I say, I take those two regions, Blue Mountains that I just talked about first, and then the Klamath, I take those two and I could separate them from the rest of Oregon. In fact, Thomas Condon, our first state geologist, separated them. He wrote a book in 1906 that was called The Two Islands, because he recognized, even way before we understood plate tectonics or how this whole thing worked, Thomas Condon recognized that the two features of areas of Oregon in the extreme northeastern corner and the extreme southwestern corner, opposite ends of the state, were very different than any of the other rocks. So different that he said it was as if they were two islands sticking up out of Oregon that were different. So that was and he recognized this. Now, this was way before we understood plate tectonics, but we do understand it now. And I can tell you that both of these regions are what we call accreted terrains. A terrain, not spelled like all-terrain vehicle, but spelled T-E-R-R-A-N-E. A terrain is a chunk of land that came from somewhere else. And through the magic of plate tectonics, it gets added onto the continent. So let me show you a diagram here that shows what's happening. We have oceanic arc. So we've got an island, I've got a volcano out here in the ocean, and through the magic of plate tectonics, it's riding on a moving plate. It is headed towards the continent, and the continent of North America at this time did not contain modern day Washington, Oregon, or even California, but actually the edge of the continent was over here in Idaho. And then those places got these accreted terrain, this foreign land is moving by the magic of plate tectonics. And what happens here at a convergent boundary is we've got a tectonic plate here, and then we've got another piece of the Earth's crust, another tectonic plate that is moving and subducting under the continental plate. But when we have an island in the way or a big landmass, it can't go down, it cannot subduct. And so instead, it gets accreted onto it. And here's that word terrain. Let's pause it right here. Okay. And so this landmass then actually, we have evidence from the fossils of the Blue Mountains and even of the Klamaths that these areas did not originate anywhere close to North America. In fact, they originated over in Asia. And the fossils from Asia, these match the fossils of Asia, not the North American fossils. Okay, so it's simply too big. Now, also volcanism happens and kind of glues and welds that whole thing together again. And now we've just added on to the edge of the continent. Okay, and this happens with successive terrains moving by the magic of moving plates over the surface of the Earth, moving those land masses and actually adding them onto the continent. So when I say that these are the oldest rocks in Oregon, that there was no Oregon. Oregon was ocean until these places were accreted on, the Blue Mountains and the Klamath Mountains. Okay, and then we've got the Basin and Range area, and this area of southeastern Oregon is known for, it's named after what it's known for, Basin and Range. Mountain ranges, parallel mountain ranges with basins in between them. So we have all the, we have mountain ranges in here that run north-south, and then in between them we have basins or low spots. Let me show you some of the lava that comes from the Basin and Range, and this is Steens Mountain basalt. And it is now recently we've discovered the relationship between it and the Columbia River basalts, which is kind of a new thing and exciting. If we look at the Steens Mountains here, the Steens Mountains bear the effects of very clearly, this picture shows this nice U-shaped valley, which bears the scars of having had glaciers come through there. The only way you get a nice U-shaped valley like this is the effect of glaciation. There's a picture of the Steens, and you can see even today, and certainly during the ice ages, there was much more extensive glaciers than there are today, but some of the glaciers still persist on the Steens Mountains in this region. Okay, this region is also known for having a lot of lakes, because those basins during the ice ages, there was much more water available and more precipitation actually, and these lakes, these places that are now dry in southern this area of Oregon used to have lakes. Therefore, there used to be people around here. It hosted more native people than would want to live there today. So simply, we've had a climate change since the last ice ages, and it's changed everything. This is another one of those lakes here showing that you could see that this is a very shallow lake, and it's just basically a puddle, a leftover puddle in all these basins in the Basin and Range.
Sheila, can I ask you a question really quickly?
Yeah.
And a good one from the chat, and I didn't know the answer. But what is the drainage situation in the Basin and Range?
Well, it's called the Basin and the Great Basin because the drainage is internal.
Okay.
And that's why we have Salt Lake. So this is just a little portion of Oregon, but the Basin and Range area extends down through Nevada and even into Mexico. And so the drainage is basically internal, and that's why Salt Lake City that's why the Great Salt Lake is so salty, because it's just basically mimicking an ocean. In other words, the water goes in and it doesn't come out. It evaporates out.
Can you field a question back from the Blue Mountains?
Okay, yeah.
Okay, because this is a good one too. How do the Blue Mountains have Asiatic fossils if the magma that moved east carrying carrying this accreted terrain came from the mid-oceanic ridge? Does that question?
It didn't. Okay, so my animation is a little bit misleading, and they will be, because they're very basic out of a textbook. So in the case of the Blue Mountains and area, there were terrains, and terrains are a chunk of land that pre-existed, was actually part of the continent of Asia, and then moving on a moving plate, but not having formed at a mid-ocean ridge.
Okay.
If it had formed at a mid-ocean ridge, you wouldn't have fossils, and you don't have fossils in igneous rock. This is sedimentary rock from a chunk of land that tore off of China and then moved by the magic of plate tectonics over. Okay, and then volcanism is involved, because then the volcanism actually welds those pieces together. Okay, so the fossil that was found primarily in the Blue Mountains that really pinned it down, and this was part of Bill Orr's research, was an animal called an Ichthyosaur, which was a gigantic reptile-like animal. It was a swimming reptile, looked like a porpoise, modern-day porpoise, but it was a reptile. And there were ichthyosaurs that lived during the age of the dinosaurs, so during the Mesozoic era. And we have them in Nevada, we have them in North America, but they also have them in Asia. Bill went over to China and investigated them and found that the ones from the Blue Mountains did not match the ones in Nevada and North America. They matched the ones in China. And just a very little detail about its spinal column that tells them that. Okay, so probably more information than you wanted to know.
No, that's great.
Okay, can I keep moving here?
Please do.
Okay, so we were talking about the lakes that existed in the Basin and Range area and these basins. And some of these, I basically see these today, they're drying up. They're in the process of drying up. And that's what they're really doing, is they're drying up not just in the last 20, 30, or even 50 or 100 years. They're drying up over the last 10,000 years, since the end of the last ice ages. So this area is known for, it was quite wet during those days, and there were lakes. These are just the remnants of the lakes. I think the most telling remnant of the extent of the lakes is Fort Rock in this area. And Fort Rock is an example of volcanism. So we've got this whole edifice here that's just basically hollow in the middle. There was volcanic action coming up through a shallow lake in this area, and it was throwing tephra, or volcanic material, in a ring all around the center. So just imagine an explosion coming out of the center here, and leaving material in a ring-like structure. And that was all happening in a shallow lake that existed during the ice ages. Today it's covered with sagebrush, but you can still see, I can see right here a bench that was cut by waves, just like ocean erosion does. When waves pour on an area, that kind of cut a bench like we have all along the coast today. And this was forming at the edge of Fort Rock. So these lakes were big enough to have waves, just very much like the ocean. Kind of incredible. And today, talk about climate change, and that's natural climate changes. We were in and out of the ice ages for the last 1.8 million years, and this is the end of the most recent glaciation. Okay, now the whole thing that's interesting about tectonically about the Basin and Range area is that it's been stretched. So in fact, this area also includes Nevada. Nevada used to be the skinny little state. It has been stretched to like twice its original width. So I'm going to show you another animation here that shows how stretching can happen. Okay, so here we have a continental crust, and then we have the asthenosphere underneath it, which is a molten, semi-molten layer of rock that the tectonic plates ride on. And so the motion here is a stretching or extension that's pulling it apart. So let's watch what happens. And it's actually happening quickly. We have hot magma coming up from deep inside the mantle in this area, and it's causing the area to rift. So we might call that a rift valley. We see one today developing in Africa. East Africa has a rift system, but this is also happening in the Basin and Range. And let me just take this animation a little bit farther, and you can see how the crust here, because it's thinner, it's being stretched and it's broken into blocks. And some of those blocks drop down. Others blocks are left standing up. So when we have some drop down, they become basins, and the ones standing up become mountain ranges. So we have the Basin and Range area here. Now, if it were to continue, this, we can just extrapolate and figure out what would happen in the future. Someday this might actually open up and become an ocean basin. But that's way down the line, and you and I do not need to lose any sleep worrying about that. Okay, so I won't take it any farther than this because this is a generalized, but I just wanted to show you the block faulting mountains that happen. And yes, some volcanic activity. I showed you the Steens basalt coming up. So we've got Basin and Range here due to extension. Okay, let's move on to the next one. And the next region is one called the high lava plains. Sometimes Fort Rock is considered part of the high lava plains. Sometimes it's considered Basin or Range because it's basically right in this area between the two. But let's look at the high lava plains, which, as you might guess, it has a lot of lava. Now I'm just going to show you, when I put the animation or the felt board together, I'm going to show you what's happening during the high lava plains, basically volcanoes, okay, spewing lava. The oldest ones are here, and the youngest one is right here in this corner, and that is near Bend. That's Newberry Volcano. So let me show you a picture of Newberry Volcano. Where's the volcano? I don't see a volcano. I see a ridge over here in the back. That's Newberry Volcano because it's what we call a shield volcano. But it does have a crater in the top of it. It's very much like the Hawaiian volcanoes, which aren't pointed like our Cascades at all. They're a different kind of lava and a different kind of mountain. But up in the center of this Newberry caldera, we could call it the big crater of caldera. It's got two lakes, East Lake and Paulina Lake. And here's another picture of it showing the big obsidian flow. This is a huge features, and that mountain is, you know, so large, and it is the youngest in a age progression of lava across the high lava plains. Another feature of that might be Lava Butte, just south of Bend, and Lava Butte is a cinder cone, so a different kind of volcano, same kind of lava as Newberry, but coming out differently and making a pile of cinders. So this is Lava Butte, just south of Bend. You might be familiar with it. And these kind of this area also has caves, but the caves of Central Oregon are lava tubes, just very much like you would see in Hawaii. So lava poured through an area and then flowed out of it, leaving a cave behind. These are very interesting. Now, the origin of the high lava plains as a province is very complicated. A lot of people working on it, and so forth. But so I'm just going to try to make it very simple to understand that it has a lot to do with the Yellowstone hotspot. And let me show you what a hotspot is under an ocean. In other words, Hawaii is a good example of this. Yellowstone is a hotspot under a continent. I don't have an animation that'll show you a hotspot under a continent, but let me just show you the basic idea of hotspot. Okay, so we've got an ocean, we've got magma that just for some reason is coming. We don't really know the origin of these hotspots, but it comes from deep inside the earth and it starts erupting, in this case under an ocean, and it forms an island. Okay, so we've got an island. Now here's the deal. Okay, why not? Here's the deal is that the hotspot basically stays in one place, but the plate moves over it. And so over time, the original island moves off, or the original volcanic structure moves off of the hotspot, and a new one forms. And then another again. And we get another island eventually. So we have what we call an age progression, which is due to a hotspot. Okay, wait, here, I'll move it. We'll do it in fast. 1 island, 2, 3. These are volcanic centers. Okay, so we have the oldest one here, and then they get progressively younger as you go in a certain direction. That's what we call an age progression. So the high lava plains, even though it was not under an ocean at this time, or it was not an oceanic setting, it was a hotspot under a continent, which makes it even more explosive. So the Hawaiian volcanoes are rather mild-mannered. Yellowstone was a super volcano, because when you come up a hotspot through a continent, you get extremely explosive activity. So that is the central portion of the state, is the high lava plains that are related indirectly to a hotspot. Okay, I want to move on here. How are we doing? Doing okay for time and everything? You guys are still with me, I hope. Okay, I can't. Come on. Let's see if I can. Okay, there, I'm sorry. Okay, now we'll go to the volcanoes that you probably recognize as volcanoes, and that's this spine down the north, running north and south throughout the state, dividing Western Oregon from Eastern Oregon. And that's the Cascades. But we'll take the Cascades and we'll talk about it we'll talk about it as if it's one range, but it's really 2 ranges. We have the older Western Cascades that started up much earlier than the mountain peaks that we see today. And they're in this region here, just between you know, the Willamette Valley and the high Cascades. We have the Western Cascades. And then we have the peaks, the familiar peaks of the Cascades now in this region we call the high Cascades. So I just took one picture of the Calipooly River coming down through the Western Cascades. So you can see that the terrain here, the Western Cascades are composed of hills because they're basically old volcanoes that have eroded down. But the new ones are coming up, and we focus on that. If we take the Cascades and look at it, how it goes through the Columbia River Gorge cuts through the Cascades, and we've got a lot, and it's been lined by lava. More on that later. The lava, where the lava came from, making places like Multnomah Falls. We want to focus on the most recent one. In fact, we're 40 years out from the 1980 eruption of Mount St. Helens. And Mount St. Helens was the youngest, one of the youngest in the Cascade Range, and certainly probably the most active in the last 4,000 years. But we also have Mount Hood, as you know, which is the backdrop of Portland. And Mount Hood, many different views of Mount Hood. It's been sculpted by glaciers, and you can see that very nicely from all the different angles of Mount Hood. It shows its face. And then we have Mount Jefferson, beautiful Mount Jefferson here. It hasn't been active in a long time, but another one of the high Cascades, Three Sisters, and so forth. And down Mount Washington, just what's all that's left of a deeply eroded cone, and then Crater Lake, a mountain that, a volcano that blew up on itself so much that it actually collapsed into itself and formed a lake here. So I'm just going to show you just a little bit about the type of volcanoes that the high Cascades are, and the Western Cascades were made out of. Now, this is a generalization because there's all kinds of activity, but the one we focus on is a composite volcano made of layers of tephra, loose material, and then lava capping it off. Tephra and lava. So these volcanoes are called composite volcanoes because they're made of layers, or sometimes they're called stratocone volcanoes, made of layers of different kinds of deposit. And that makes that beautiful cone shape that you recognize. Most people recognize that as a volcano. Okay, I can't seem to advance the slide. Hold on here. There we go. Okay, now we'll talk about another kind of volcano that covers this region of Oregon, the Deschutes Columbia Plateau. Most of the Columbia Plateau is up in Washington. This is a little piece of it that sticks down into Oregon, and it's made of lava flows. The source and the origin of this lava is right along here, our border between Oregon and Idaho and Washington and Idaho. Several bends through here spewing lava, and I'm sure you've probably heard of the Columbia River basalts, and this Deschutes Columbia Plateau is just basalt layer on basalt layer. So you can see here kind of a plateau because it's flat top, because igneous rock. This lava, instead of making a cone, just pours over the landscape and makes a flat area that's very durable and hard to erode, so it stays, it goes the distance. You can see here the nice, we've got some Cascades in the background, or some different mountains in the background, but here we have this nice flat area, and that's capped by, this is all lava flows, one lava flow after another. Some of these lava flows were enormous in size to the point where they were lava flow 100 feet thick. Think of a wall of red lava advancing towards you that's 100 feet thick. You get, it cools in columns like we have here. So you can see all the different columns. We're looking at several different layers here. And yes, it has been eroded, but it's hard to erode. But this erosion that has happened here is exposing the columns in a nice way. So this whole Deschutes Columbia Plateau is just made of lava flow after lava flow. The enormous Columbia River basalts basically followed the course of the Columbia River. Actually moved the river over. Okay, then we'll talk about our coast range. So what we're getting into more recent stuff here, and we've got some high peaks in the coast range, not nearly as high as the Cascades, and these are not volcanic in nature. There's no active volcanism, or never was active volcanism to make the coast range. I won't say never, because the base of the coast range is basalt that erupted offshore and now forms the high spot. So this is Saddle Mountain, and which is a high spot. The other high spot that we took a field trip to last year was Mary's Peak, and it is also made of this basalt that forms the basement rocks of the Coast Range. But most of the Coast Range is sandstone, and this is a predominant one. This is an exposure of the Tyee sandstone. You can see great big chunks of this, the layers and layers of sandstone that have then been folded up to form our Coast Range today. And of course, the Coast Range includes the coast, and I've got this beautiful picture here of Hug Point. You might recognize it. These folks are walking on a road that during stagecoach days, this was a stagecoach road, a way to get around there during low tide. And they had to have a way to get around here. Our whole Oregon coast is armored with basalt. Some of these are Columbia River basalts. Others are more local basalt, but then the sandstone is also the main rock of the Coast Range. I've got a picture here that I took of Boiler Bay, and you can see the folding that's occurred in here. So this exposes it nicely, and you can see the folding in the sandstone. now I don't have another picture of some of the capes along the Oregon coast. Okay, now I don't have an animation from it, but I have these wonderful illustrations from Bill Orr's book on the origin and the Coast Range. And so let's just kind of review it here. We're looking to the south in this direction. So we've got modern day Portland right here, modern day Salem and Eugene. And then we have the Klamath Mountains in southern Oregon over here. Now this whole area right here, I'm tracing the old shoreline during those times. And this was during the middle to late Eocene. So around 40 million years ago to about 35 million years ago, or maybe 30 to 40 million years ago, Oregon, this part of Oregon did not exist. And our shoreline was over here just in the Scotts Mills area or the Silverton area. Now, the Klamath Mountains, though, existed in this part of the state, and they were eroding the sandstone, this is the Tyee sandstone, into this bay. And then, and let's fast forward in time. And over time, because subduction is going on, more about that later, but we've got a subduction zone here where the one plate is diving under us, and it's kind of lifting this area up. So we get into about 25 million years ago, and now that has been lifted up, but we still have a bay. And in fact, modern day Eugene and Salem are still underwater. Portland is largely underwater, but it's got some boring volcanics from the boring area. They're not boring, they're very interesting, but we've got some local volcanics here going on as well. And then finally, this gets uplifted by the Miocene times by about 15 million years ago. Then it's becoming more of a shoreline like we have today. So the origin of the Coast Range. And then finally, we'll end with our little neck of the woods, the Willamette Valley. Willamette Valley is known to host the Willamette River. Now, the Willamette Valley exists there. It exists, but not because of structural things that are going on. The Willamette River did not carve out the Willamette Valley, in other words, but it merely occupies the low spot in between two mountain ranges. We're wedged in between the Cascades on the east and the Coast Range on the west. And as you know, the Willamette Valley is famous for the soil. Just since the 90s, this turned into vineyard land. We've got some hills in the Willamette Valley, and that's part of that Columbia River basalt now, that same rock that makes up Multnomah Falls and the Deschutes Columbia Plateau. Some of it moved into the Willamette Valley and forms the higher spots here, the Amity Hills, the Eola Hills, and so forth. And another picture, and of course, then we have the Portland area is, you know, the uppermost, northernmost region of the Willamette Valley, and it's got all these hills. This is all the boring volcanics that you're seeing in the background here. And then, of course, the vineyards and lots of pictures of them. Now, one thing you might not know of the Willamette Valley is it's known for its fossils. Now, these are the most recent fossils on the scene. These are Ice Age fossils. This is the dig that happens in Woodburn, near the Woodburn High School about 10 years ago. And we're finding it's recovering bones that have been preserved in the peat, peat there. So the Willamette Valley is basically, like during the Ice Age, was big wetlands, and it hosts a lot of fossils as well. So most people don't realize that. They don't think of fossils as being so prevalent here in the Willamette Valley. Okay, do we have any questions here that we want to field before I just wrap this up, and then I'll put the felt board on?
Well, I think we had, this is a great question.
Okay.
From Mike Goodman. Why are there no areas of coastal plain along the Pacific Ocean the way there are on the Atlantic coast?
Oh, wonderful question.
Is that a fungo? Is that a softball question for you, Sheila?
That's a wonderful question, because that's actually what I noticed and how my first geology class put it all together for me. I had lived on the East Coast, so yeah, they have wonderful coastal plain. The difference is the type of boundary that we're on, type of tectonic boundary. The East Coast is not on the boundary of a plate. It's in the middle of a plate. The boundary is the mid-Atlantic ridge in the middle of the Atlantic Ocean. And so because it's pulling apart there at what we call a divergent boundary, the Atlantic Ocean is getting wider and spreading, and the coast is just along for the ride. Now the West Coast has a convergent boundary where two plates are coming together, and the one plate dives under the other one in this process called subduction, which is everything why the West Coast is so very different. And so our coast is being lifted up. And then on top of it, it's been inundated by lava from various sources. And that's why the Oregon coast looks so different than the East Coast.
Good. Well, we're at our hour mark, and we had some really interesting conversation in the chat about Iceland, but I think we should kind of postpone that.
I could do Iceland. I'm going to get Scott Burns to do Iceland.
Yeah, I think we might be able to get Scott Burns to do a lecture on Iceland. He was just there recently. So,
yeah.
I've got a screenshot ready that's relevant to the coastal plain question.
Okay, let me finish this and then I'll let you share it. And before I get to, okay, can we do that?
Yeah, let's wrap up with the felt.
Let's
see the whole thing in felt.
Okay, what I put this in at the last minute because I really want to, if we had one kind of geologic process that characterizes Oregon, I would have to say it's volcanics. So Oregon has a very volcanic history. It's all about volcanoes and not just the Cascades. I mean, you know the Cascades are volcanoes, but look at the accreted terrains of the Blue Mountains and the Klamath Mountains. They were formed by, in some cases, they were offshore volcanoes. And they've certainly been stitched together by this process of accretion, which brings plutonic igneous rock to the surface and glues them together. So we've got that. We've got the Basin and Range, which is all about extension. And when you pull the Earth's crust apart, you get the hot stuff that's underneath it comes closer to the surface. So we have a lot of hydrothermal features in the Basin and Range. I should have mentioned that. We have a lot of hot springs there because the lava is so close to the surface there because this area has been stretched. Then we have the Deschutes Columbia Plateau, which is solid lava, these gigantic cracks that opened up in the ground along the Oregon-Idaho border that just poured out lava over this whole region of the West Coast. And then even the mild-mannered high lava plains, what can I say? I mean, that's obviously lava. You know, we've got lava after lava of different types and different kind of volcanism going on. Even the mild-mannered Coast Range, which really is not volcanic at all, but it's built on a solid block of volcanic material. So I have to say, and the Oregon's volcanic history is also means for preserving the John Day fossil beds and all the other wonderful sedimentary features that we have is all due to the lava. So I've got a couple of animations that I just found recently and I want to share them with you.
Before you do, and a couple people are dropping off, I wanted to make sure that we answer the question for a lot of our beginners.
Okay, go ahead.
What are the best, you've been teaching geology on an introductory level. What are the best sources of for people who are just starting? What are the best books? And some people might put this in the chat too, but what would you recommend? Well,
I think some of the, when I first started teaching geology of Oregon, we were using Bill Orr's book, the Oregon Geology or Geology of Oregon. That is the best overall information on the state of Oregon.
Carol is trying to hold it up, but she's got a virtual background on it.
Let me get rid of that.
Okay.
Okay, so there's
the book.
Here's the most recent edition, and most of those wonderful drawings and illustrations that you saw are by Bill and Elizabeth. So you can see there that there. But when we started teaching, I started teaching with Bill Orr. We were using Geology Oregon. It's a little, you have to have some geologic knowledge to really understand it very well. Yeah, there's the original Ewart Collins.
It's actually the second edition.
Yeah, that's the second edition. So I would say any introductory textbook. And the one I use, let me see if I can get it out. I'm right here in my library. I really like this one. So I think if you're interested in the geology of Oregon or the Pacific Northwest, go with Bill's books. Or Marley Miller's book, Roadside Geology, as well. But
Carol, get that one there.
Well, I'm looking for it.
This one is just a basic Essentials of Geology by Tarbuck and Lugans, and this just gives you, yeah, there's Marley Miller's book. And then this one, oh God, I can't seem to, here, there we go. Oh, okay, forget where the camera was. Okay, this is a nice book. I use this as a textbook for 101 geology.
Okay, and someone else says Ellen Morris Bishop's, and Carol's holding it up just on time. In Search of Beautiful book.
Ancient Oregon has got wonderful photography and good, but you probably need to have a background in geology for beginners if you're brand new to geology. Mm-hmm. You want to get some idea, and you can start Googling things too.
Okay, so Sheila, in the time we have remaining, can you do your whole lecture again, but in felt?
Yeah, I'll do it in felt. Let me show you, let me share these animations, and then we'll let Dennis share what he had, and then I'll go to felt. Okay, so let me see. Okay, so I just found these, which shows the convection that's going on. In other words, the currents that are going on underneath the Earth's crust. And I don't know why I've never used these in class. I never noticed it before, but we've got, you know, spreading going apart here at a mid-ocean ridge. So we call this a divergent boundary, but here we have two plates coming together and we have a convergent boundary with a subduction zone. But so we're seeing part of the action here with the crust of the Earth's rock going back in, melting, and then coming back up again. It's kind of cool. And then another one that I want to show you is, this one is a good one for the origin of the Cascades and what we think of as your typical volcano. And this is for the very beginners in geology. This is one of the coolest things. We got one plate diving under another. When it gets down here, because it's carrying water, it's melting some of the rocks, which is creating a magma chamber and then a volcanic arc on top of it. In other words, a chain of volcanoes. And think of the Cascades as a chain of volcanoes coming not through the ocean, but coming up through a continent. But the same process going on. So that's a nice little animation there. Okay, I'm going to stop sharing and let somebody else share. Are you still with me? Oh, okay, I can't see you guys when I'm talking, but good to see your faces now. You're still with me.
Sheila, there were a couple more questions. One was about whether there are terrains from the Baja up in Oregon. And the other one was asking about the source of the Tyee Formation. They had heard that there might be some material from Idaho.
Oh, yeah.
Okay.
Let me address the Tyee Formation first. Yeah, what tells us that the Tyee Formation, which is eroded from the Klamath Mountains, but what tells us that it was actually, I'm going to get to that when I do the felt board. It actually accreted to Idaho. Okay, because there are muscovite flakes in there, which are from the Idaho batholith, or the rock that's real prevalent in Idaho, has a mineral called muscovite, and the little muscovite flakes in the Tyee sandstone are very apparent, and they have been traced to Idaho, believe it or not. So we'll talk about that and that conundrum that happens when I put together the felt board. Okay, the other question, would you mind repeating the other question?
They asked whether there was some terrains from the Baja up in Oregon.
You've been listening to Nick, right? Yeah. Yes. Yes, there are. And I've got a wonderful animation. Let's do it at another meetup. That I've got a paper animation that was made by Tanya Atwater, and she gave it to me. She did the research on the San Andreas Fault. She's famous for that, and she shows that stuff moving upward, moving northward.
Wait, I got to interrupt.
Okay.
This is the BC to Baja theory. There are Baja terrains in Oregon.
Not in Oregon, but up in Washington.
Up in Washington.
Oregon has the old remnant of the Farallon plate, which is now called the Juan Fuca plate, kind of shoved in between it. Mm-hmm. But if you look at the whole West Coast from Baja, California, all the way up to Alaska, except for the Juan Fuca plate, which is here in Oregon and Washington, we've got the San Andreas Fault running through California, and then an extension of it up in the north called the Queen Charlotte Fault. Same motion. So that area. Now, how the Farallon fits into that time-wise, Nick was not real.
Sorry, I led you down that path.
Yeah,
but that's okay. So
there's so many. Students tell me, "Gee, you know everything about geology. What else is there to learn?" I said, "Tons." Because there's still a lot of enigmas that we have not answered.
Right.
And that are, so we're looking at the evidence, but trying to find a model that puts it all together, it's still, still.
I actually put a reference to some people that have been trying to explain the terrains around the, what is it, what islands? The Friday Harbor,
the San Juan Islands.
Yeah, the San Juan Islands,
yeah.
That's in the lecture that Marley Miller did. I looked up a reference, and you can kind of start there and start unraveling that.
Oh yeah, it's very very similar to the Klamath Mountains, and the rock is very similar. Vancouver Island, very much like the Klamaths. I lived down in the Klamaths for 14 years, so I'm wandered around all those woods and looked at all the rocks and very similar to it. So because it's all that accreted terrain. So I'll get to that when I talk about the felt board. Did you want to take a break here? And Dennis, did you have something you wanted to show us? Share.
Am I muted?
Did I stop sharing?
No.
I think I did.
I'm here.
Right?
Yeah. There was a question earlier about having to do with the coastal plain.
Oh yeah.
Yeah.
I already answered it. Yeah.
Coastal plain on the East Coast, and I have a screenshot on Google Earth here that I think shows some of the differences.
Go ahead and share it with us.
On the West Coast. Up here is Astoria, where the cursor is, and offshore we can see.
You're not sharing it, or at least I'm not seeing it.
Oh, I'm sorry, just a minute.
You have to share, go to share screen, and then you have to pick the screen you want to share, and then you have to push the share button. That's in the lower, there you go.
You see that?
Yeah.
Okay. And this, I think, is showing evidence of the Juan Fuca Ridge, which is spreading apart along this axis here.
Spreading, yes.
A transform fault that connects it to another ridge that is down here off screen. We can't see the profile here, but this would be the, I guess, the continental shelf.
That's a continental shelf, and then just to the left of it is the continental rise until or slope until you get down to right here where the slope. I don't know if you can. You probably can't see my arrow because I'm not sharing, but right at the contact between that and the deep flat ocean floor, that's the subduction zone.
Okay. And this, I think, is particularly interesting. This is a submarine canyon that was cut by the discharge from the Columbia River.
Yes,
but
that's
these blocks here,
Canyon. Yes.
When I see these blocks, what I think I'm seeing is stuff being jammed up against the the continent.
Yeah, there's still stuff under there, you know, just like, actually, I didn't mention the Saluzzi block, but I will. It forms the basement of the Coast Range. And there's still a lot of stuff out there that just doesn't get into the subduction zone. It just can't get, it can't subduct under. So it's getting kind of stuck under there, half accreted, you might say. It doesn't stick up above land, but it's there.
You know, this might be a rather young version of some of the things that were pushed up on land that we saw on the Klamath field trip.
Denny, that's fascinating. I've never noticed that.
Oh yeah.
I mean, are we basically?
We could do a whole Google Earth, and then if you go over to the Mid-Atlantic Ridge and scroll all the way over to the East Coast, you'll see that the East Coast is not on a plate boundary. It's right in the middle of the plate.
Yeah, you don't see anything like this on the east.
Yeah, it's kind of the trailing edge of the continent. So very different, very different.
Sheila, I think we might have to save the felt board for another time.
Okay.
We're past our hour, and it would be nice to take some questions. We've had some great ones.
Okay.
Someone asked about the Kula plate.
Yeah.
What happened to the Kula plate?
It's gone.
It's gone.
That's what Kula means, I guess, all gone. It's basically was moving northward and totally subducted under.
Okay.
And so, but we think that that's what's dragging the movement along the Queen Charlotte Fault.
Oh, I see. Okay.
Yeah.
And was there a transformed spreading center between the Kula and the Farallon that was subducted?
Yes. Yeah, there would have had to be. The Kula was moving north and it's basically subducted all the way under. The Farallon plate is moving kind of northeast. And so it's not just moving directly east into us. It's basically moving, it's oblique subduction, moving northeast. And there was some kind of spreading center along there, yes. Okay. In fact, it's theorized that the rocks along the Oregon coast, part of the Siletz River basalts were formed from that spreading center.
Ah, okay.
That was an idea. I think they kind of canned that idea, but that's an interesting idea. So in other words, you've got volcanism. I don't know if you can see, but you have volcanism on both sides of a spreading center. You know, and we think that some of the rocks like Cascade Rock, Cascade Head, which is old Eocene basalt, not Columbia River basalt along the Oregon coast. And there's an age progression there that, and so there was an idea that that spreading caused the volcanoes that are offshore. And then the Farallon plate moved them into Oregon and smashed them under Oregon.
Okay.
So you can see them in places like Elk Rock and some of the places you go in the Portland tour.
Okay, thank you. You've pointed that out to me before, but I hadn't put that together with that story.
Yeah, so, I saw that light bulb go off in your head.
Yeah, I was like, okay. Well, that is a wonderful.
This is like, you know, when you see the light bulb go off in their head, it's like, this is fun. So
that's the best.
Do people want to stay and I'll go ahead and put together the felt board? It'd probably only take about 10 minutes, but if you're, you know, we could take a break here.
I'm going to stay. I'll stay. Let's do it.
You want to do it?
Let's do it. Let's see the felt. People are giving, I'm seeing thumbs up, so.
I can do the quick version. Let me get my office arranged.
Don't forget to stand as close as you can to the mic.
Yeah, I know. That's why I had to move the chair I was sitting in. Okay, probably got a nice view of my back there.
Okay, Danny, we'll see you later.
How's that look?
That's good.
Is that good? I don't like the lighting. Okay. Now, you can put me on speaker view. You can toggle between gallery view and speaker view, so I'm not a little thumbnail. So my screen is bigger. Okay. Okay. So let's go ahead and do it. We'll start with the oldest rocks in Oregon, which were the
Blue Mountains and Klamath.
Mountains. Okay. So I've got the Blue Mountains here. I want to show you that the Blue Mountains is really a collection of terrains. Okay, so the Blue Mountain is all accreted terrains, plural. In other words, so we've got the Old Ferry, the Wallowa terrain, the Baker terrain, the IZ for 4 of them. And basically you can see that they're all kind of stitched together here because they amalgamated is what they did. In other words, they accreted to each other before they actually accreted onto the continent. Okay, so we'll move them over to the Idaho border where they rest today. And that's the Blue Mountains. Let me play with the light a little and see if light coming in from this window makes it better or worse. Does that make it better for you folks or worse?
That's good. I can see it.
Yeah.
I love the stitching.
Yeah, that's Staples. I'm felt pieces. Okay. Okay, now the Klamath Mountains, again, the question on the relationship between it and the Idaho batholith is because the Klamath Mountains, they're the stuff coming off of the Tyee has evidence that it had minerals from the Idaho batholith. So we believe that the Klamaths first formed and accreted on somewhere in there. This is Idaho. Okay, now you might ask, and here's an enigma that I can't quite answer, and I know people are working on it and geologists argue over it. How did it end up way over here where it is today?
Oh, wait, I know.
You have another idea like many, but let me, bear with me here,
Okay.
And let's see if I answer your question. Okay, remember we've got the Basin and Range in here, and the Basin and Range is due to extension, and this is at the other end of it. Now the time doesn't quite work out because the Basin and Range started spreading in the Miocene, but anyway, there's an enigma. But the Basin and Range is fault block mountains. So we've got mountain ranges sticking up, basins in between them. And some of those basins were filled with lakes and so forth. Stretching going on. So a lot of heat being produced here has the potential for geothermal energy, which is which is what they use in Iceland and which is wonderful. We have the potential over here because the crust is thin. Okay. Then what happens? Well, now this is not all happening in chronological order exactly because there's a lot of things going on at the same time. Okay, so don't say this is an exact chronology. It isn't. Okay, the next region is the high lava plains. We'll put them in here. And as I said, this is an age progression. Let's see if I can get my Blue Mountains getting a little bit better. Okay, I love the plains, be right here. Okay, now we've got an age progression. So we've got the oldest volcanics here, and then they get progressively younger until you get all the way here to Newberry. Okay, in fact, one thing I want to mention is Prineville and the Crooked River caldera are part of this age progression right in here, or right about in here, I guess. And you know, and I want to show you now the Yellowstone hotspot is marching off to Yellowstone. So we've got lava moving the other direction. So we have volcanism all along the Snake River Plain in Idaho to its present day location at Yellowstone today. So how do we have lava going, an age progression going this way with the youngest in Yellowstone and an age progression going this way? The answer that made most sense to me is when I look at Hawaii. So if you go to the big island of Hawaii, that's where all the active lava is coming out and stuff. But we have remnant, and Hawaii is the one that's present day on the hotspot. Before that, Maui was, and before that, Oahu is. Both Maui and Oahu have remnant volcanism. There's Haleakala Crater on Maui, and then there's Diamond Head on Oahu, which is recent. So we have lava basically in Hawaii spreading back the other way. So we've got things going on here, subduction and so forth. It's basically, I'm going to say it in a very loose general sense, it is kind of some of the leftover stuff from the Yellowstone hotspot. Okay, so the lava basically smearing back the other way as the plate is going over it. I don't know if that explains it. There's a lot to work out. Okay, now we have the west, somewhere in here, we have the Western Cascades. Where did I put these? Okay, so we had active volcanism going on too at that time, and so forth. Okay, what was going on with the Klamaths? So we have a chain of volcanoes here, the Western Cascades, which are now eroded down. This is places like Silverton and places like Brownsville and Lebanon. All these places are in the remains of older volcanoes. The present day high Cascades are here, but I'm not putting them in just yet. Okay, then the Tyee Delta erosion from the Klamath Mountains. This, remember, look at the shoreline, except for what's in here, which I could cover up. Actually, if we can, this, let's do this. This one goes next. Okay, we have volcanism in the high lava plains, and then that puts the John Day, the Clarno, first the Clarno, and then the John Day Formation on top of the Blue Mountains. Okay, so now we basically have Oregon, except for this big bay that existed of Western Oregon. Let's fill it in. The Klamath Mountains are eroding into sandstone, and little, like I said, little muscovite flakes from that sandstone belong way over there in Idaho. So there's the idea that this actually accreted over here, and then this stuff is shedding into the embayment today. Okay, this gets folded up into the Coast Range. We put a Coast Range here. Okay, and then we had, then comes the lava. Okay, so we've got the whole thing is, let's see, the Deschutes Columbia Plateau and the lava. I don't remember exactly how I had this here. Okay, the volcanism from the Western Cascades has shifted to the east, and we have the peaks of the high Cascades. Now we have lava. So look at the Blue Mountains areas. We have accreted terrain under it, then Clarno and John Day on top of this portion of it, and then lava on top of it. I think you saw that at Sheep Rock. Remember I showed you the sequence there? Okay, so that's what we've got there. Some of this lava, remember this lava comes from the cracks that opened up along the border, the Oregon-Idaho border here, poured immense quantities of lava, not only into Oregon, but up into Washington. A lot of that comes into the Willamette Valley. I think I need to, let's see, maybe it goes this way. This way. High Cascades just fell off. Okay.
Oh no, that's a terrible disaster.
Yeah,
the entire Cascade Range just fell into California.
To come and help me hold it. So
we're going to get questions about that.
Okay, yeah. Well, anyway, this stuff comes into the Willamette Valley. Okay, and forms the Amity Hills, the Ola Hills, the Salem Hills. Okay, some of it flows all the way out the Columbia River to Astoria, and then amazingly, come on, stay up here. I'll put it back here like that. Okay, amazingly forms the headlands along the coast all the way down to Seal Rock. So all, now not every headland, because there's some other ones, but things like Cape Lookout, Cape Meares, those are all Columbia River basalt that flowed down, covered the plateau, flowed down the Columbia River, makes Multnomah Falls, flowed out to Astoria, and then we've got it all the way down here to Seal Rock. Okay, now I know that there had to be strings of it going through the Coast Range, and that's what I've centered my research on, and I've been unsuccessful at matching it chemically to the Columbia River basalt so far. So there's a problem there. Maybe, you know, we haven't worked that out. And then the Willamette Valley is wedged in between it. The latest thing with the Willamette Valley, of course, was the Missoula Floods, which I didn't talk about, but they come in and bring in all the wonderful farm soil that makes this the most populated part of Oregon today. Okay.